The last two lectures were the introduction to coordination compounds, and I showed you all kinds of fun little structures, and now we have to do something a little bit less pleasant, which is nomenclature. We're going to need to learn how to name these compounds properly, because that's part of chemistry. And to make it just a little bit of fun, we're going to draw some isomers of these coordination compounds. And so for example, without having taught anything to you, if you were to name this coordination compound, you have enough experience to kind of figure this out. So here we have two metal centers. They each have ligands, and then we have a bridging ligand. So all of that needs to be communicated. The name of the ligands, how many there are, and so if you do look at that, the name below, it does make sense, right? So we have here, we have tetra, which we know from organic or even from Gen Chem. This is a prefix meaning 4, and then I told you that amine, this is what we call the ammonia ligand when it's coordinated to a transition metal. So we have 4 amine ligands here, tetraamine, and then the metal center is cobalt, and giving that a Roman numeral 3 also shouldn't be a surprise to you, so that makes perfect sense. So this is a cobalt 3 center, and it has 4 amine ligands, and then this dash mu dash amido up until we get back to tetra, which is another prefix. So that must be that bridging ligand, right? Because there's nothing else attached to that first cobalt center. So dash mu dash, that must mean this is a bridging ligand, and that's exactly what that is. And so that is, amido is the ligand, so this is an amide, which has a negative charge, so that's implied by the ending here. And then we have tetra, 4 of something, 1, 2, 3, 4, that's water. We call water aqua, also not a big deal here. So those are the water ligands. And then well, it's aqua, and then I cut it off here in the wrong place. So there's a carbonyl, and we talked about carbonyl ligands. So those are the neutral carbon monoxide, and then also having to communicate the space, the oxidation state or charge of the metal. So we have an overall +6 charge, +3 for each cobalt, but then I have a space here, and it's called chloride, and so that must mean, like, we have one long word, no spaces, and since there is no other ligand shown, chloride also implies Cl-. And the other question becomes, if I ask you to, well, this isn't, not everything is shown here, right? We have a structure, but what's missing here is, if it has a counter ion, this whole thing's going to have a charge, right? And so as you would for iron 3 chloride, if I give you iron 3 chloride, you know that we have 3 chloride counter ions, right? So it just says chloride, doesn't say di or trichloride. So when I say chloride here, that doesn't mean there's just one. So that's something else that you need to pay attention to. So now, based on the ligand names, you knowing that all of these amines are neutral, okay, and you knowing the charge of the cobalt, and I told you that this right here has a negative charge, the carbonyl ligand is just 0 or neutral. And what about those aqua ligands? If you had to figure it out, obviously water is not charged. You can use the method of disconnection to figure that out, but you know, this is just an aqua water ligand, and so it's neutral. So the only thing that has a negative charge is the amide here, and there's just 1, and if the cobalts are +6, we need 5 chloride counter ions. So that's also something important that you might want to remember. But we're going to come back and start with basic simple rules. I just wanted to show you that it's not overly complicated to look at a name and figure out what the structure might be, because you already have a lot of chemistry under your belt where you would be able to make sense of it. All right. So, but before we go into all of the rules about naming, we're going to draw some isomers of these coordination compounds. All right. You remember isomers from geometry. They have the same chemical composition, just different structural arrangements. And we already looked at octahedron. So octahedron and square planar geometries can have cis and trans, right? So we know cis and trans from organic. And then I mentioned if we have 3 of the same type of ligand, we can have meridial and facial. And so one of the things that you need to do, that I highly recommend that you do when you draw these isomers, is that you select a way to draw that, right? So the way I have it here, your skeleton, and you can leave the metal out to focus on the geometry when I ask you to do that, right? So I'm just gonna draw this grid like that. That's my octahedron, where these are in the plane of the board. And then think about it. You can put 2 ligands cis in many, many different ways, right? You can also put the 2 ligands here. That's cis. And so if we had, let's say these are all other ligands. O, you know, just for argument's sake, right? So if you draw these 2 structures like that, they're actually identical. So you moving around those cis ligands are gonna mess you up. So what you want to do is you want to draw it in the same geometry and the same shape, the same way. And then if you have 2 of the same type of ligand, and then let's say 4 others, then you want to always put those in the same position here or here, whatever you want. But don't move those around. Keep them put, and then play around with the other ligands. Now we're gonna do some examples where I show you this, and then you move on to trans and you do the same thing. And here with trans too, you can put them here or here. So if you're not consistent, if you don't find a method, it's possible that you mess yourself up. Another way to draw the skeleton is like this, where we now have 2 of them coming towards us, and then 2 groups going to the back. So the only thing that's in the plane of the board are these here, okay? The z-axis, if you wish. And so it's up to you how you draw it, and do not switch between the 2. That's not a good idea. And just be consistent. And so we'll come back and I'll highlight some of those methods. So we have cis and trans, facial and meridial, some of those geometries you have to keep in mind. So we're gonna just practice drawing isomers for these examples here. Let's just go through it one by one, right? So this first one, what you want to do is determine its shape. So if we have 4 attached ligands, we have 2 potential geometries, square planar and tetrahedral. But we do know that for palladium we can only have square planar. So I do expect you to know this as well. So if I don't give you any guidance, such as draw all isomers for square planar only, if this was nickel, you would have to give me all isomers for tetrahedral, which there would just be 1, and then the 2 cis and trans isomers for nickel. So all of them should be included. But in this case, we know we have square planar only, and so it's either cis or trans. And so feel free, you know, to kind of abbreviate as you wish. And then in this case, it's, if you have the metal, that's fine. If you leave the metal out, I'll take that. But make sure it looks square planar. And then the other isomer, of course, we now put the 2 chloro ligands in the trans position here. And then I'll just include all of the phenyl groups as well, and so the triphenylphosphine is here. So those are just the only 2 examples. We have cis and trans, that's all there is. Here we have trichloro and triamino, and then you can also figure out the oxidation state here, right? These are neutral, this is negatively charged, so this would be cobalt 3, but that's besides the point. So now we have 3 of the same kind, and so we're going to end up with facial and meridial. So I draw my structures like this. This is usually what I do. And so I'll just draw my skeleton here, and this is just going to be facial and meridial, and you are done. And so I'm going to put the amine ligands here, facial, and then the chloro are also going to be facial, and then meridial would be this way, and then both the ammonia or the amine ligands as well are also meridial, right? So in one plane, right? There's a plane that cuts through there, and that's it. There's just two isomers. And again, I want to highlight that if you just move these ligands around, like let's say you put 3 chloroligands here, you still have the same skeleton, but it looks different, but it really isn't, because all you have to do is rotate that. See that those two are going to be identical. And that's why you need to have a method where you don't move things around, because you could end up drawing 5 or 6 isomers that look different but that really are the same. So the ultimate proof is when you have your model kit and you put it together, and then you can rearrange it to superimpose it. And I'm going to show you that in a minute as well. All right, so don't do that. This is really it. This is the only way we can come up with isomers. So this one here has 2 potassium ions, but we can ignore them because they're just counter ions. And so we have still 6 ligands. We have octahedron. I'm going to go with my orientation, my preferred orientation, which is like this. This time I'm going to leave the cobalt out. And since we have the highest number of the same kind of ligand is the chloro, I am going to choose either facial or meridial. And so so let's go through just facial first. The 3 chloroligands are going to stay right there. And then I have bromo, which I can either put this way, or I can put them, and that just because I'm playing around and looking at this possibility doesn't mean that what I'm about to draw is any different. Okay, so these are facial and these are both cis, so you risk that you're either drawing a redundant isomer or you might actually have stereoisomer. So if you lack any kind of mirror planes, if you draw, for example, if you draw it like this and you don't have any mirror planes, you will have a stereoisomer. So there is going to be a different orientation. And if that's the case, then you don't need to redraw it in the proper form. You just need to circle it. But for now, we do have a mirror plane, right? So back to point group theory. If you go through here and you cut through the chloro metal bond here, and then I guess in the amine. So if you have an axis that goes through the chloro, cobalt, amine axes and dissects, that would be a mirror plane. So you don't even have to consider what you've drawn here. That is going to be the same thing. These two that you've drawn are equal. And so all you have to do is find the C3 through the facial orientation, rotate that by 120 degrees, and you are back to this orientation. So this is no different. So we really just have one facial here, and then if we draw it meridial, now we can have different ways to attach the amine, because now we have a possibility of having the amine ligands, sorry, the bromos are the ones that are there in pairs of 2, so we can have the bromo in trans, or we can have bromo as cis. Okay, so again, if you are drawing to cis, bromo, or whatever you have, you want to look for mirror planes, right? Because it's possible that if I put these two bridges, that if I exchange these, it looks different, but it may not be. And so do we have a mirror plane here? And the answer is yes. All right, so for the cis orientation, that mirror plane goes right through the plane of the board, right? See these everything here except the 2 chloros are on the mirror plane, are on that plane I drew, and then the chloros would project into each other. So this is the only other isomer. So there are just 3 isomers in this case. So you do see it's tricky. You do have to pay attention to it. And so for the next one, we're going to see some stereoisomers, right? So now we have 2, 2, and 2. We still have an octahedron. We can ignore the potassium counter ion. And so I suggest that you start with one of the cis ligands, put them in the same spot. Okay. So I'm just gonna go with the chloros. I'm gonna put the two chloros here, and I'm gonna just play around with that orientation. You know, maybe there's 3, maybe there's 4, maybe there's 5. We'll find out. And then when I'm done, I'm gonna go and draw that same orientation, and this time put the chloros across from each other, just like that. Okay, so let's start with cis. So here we have cis, so the chloros are there, they're not going to be moved. And now move on to the bromos. The bromos can either be cis or trans. So if I put them here, bromo, bromo, or bromo, bromo, then the amine ligands here would have to be cis, and here they would be trans. Okay, we do have a mirror plane here, so there's no other orientation. So now I'm going to put everything cis, NH3, NH3, and then Br, and then Br. And so this molecule here, if they're all cis, 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 and you might want to label this. So we're gonna go from chloro. This is our first pair, second pair, third pair. So if I call something, so I'm going to look at the chloros, I'm going to say cis. And then this is not the way you name them, but this is just a way for us to keep straight which pair we made cis or trans. Then we move on to the bromos. The bromos are trans. And then the amines are cis. So I'm just going to call this cis, trans, cis. And then this I'm going to call cis. And then my bromos are cis. And my amines are trans. So that I don't redraw something accidentally. And this is going to be cis, cis, and cis. So for the cis, cis, and cis, if we look for mirror planes, we don't have any. So there is a stereoisomer. So instead of you can do it, you can draw it. And the best way to do it would be, let's see, I'm going to put these in cis. I'm going to take these two groups and exchange them. All right? So I'm going to keep the NH3 here and the Br here, and I'm going to just exchange them. Br and H3N. This is also cis, cis, and cis. But these are stereoisomers with respect to each other, and we only know this because we don't have any mirror planes. But I suggest that what you do, instead of drawing that, you simply circle that, which indicates to me that those are stereo. We have stereoisomers here, cis and trans isomers, and that's really it for cis, for the cis, for the chloros. All right. So if we put them here, you can play around with it, and I really highly recommend that you build it once again to come up with different geometries. So there's no other way to put this. Okay. So just these 4. So for the next combination here, we can have everything in trans, for example, here. Now we can put the bromos and the amines and the amines in the trans position here. So this is trans, trans, trans. And then I can put the bromos and the amines cis. And we do have a mirror plane, so we don't have any stereoisomers. And so let's see if there's one other one here. So if we put the chloros, we're keeping the chloros here. And then we've got trans, trans, trans. We have trans, cis, and cis. So can we put anything cis and trans? No. So this is the end of the line here. So we had a total of 5 isomers, one of them which was Stereoactive, it was the cis one. So here I've just kind of shown you how we would do it, right? If we drew this mirror image in the middle, this is how they would project. However, I don't recommend that you do this. I don't recommend, because this is a different orientation, right? By you rotating this by 180 degrees, it has a different orientation. I want you to keep everything the same. But just for demonstration purposes here, a better way to look at it, and I showed you this, is if you just simply exchange two of these ligands here, the bromo and the amine are exchanged. And so if I rotated that now, if I superimpose them, you can see, switch out those two groups, and then they don't superimpose, so you see how that works. All right, so let's go through some other types of isomers that you might encounter that you should remember. So we have these conformational isomers. I already mentioned that if you had nickel for 4 coordinate, you can have either tetrahedral or square planar. So consider that. The same is true for trigonal bipyramid or coordination number 5 and square pyramidal. Unless I specify, you need to not assume that it's only trigonal bipyramidal. But if you have 5 attached, you should draw a set of isomers for trigonal bipyramidal as well as square pyramidal. We also have coordination isomers, and that's when we have the cation and the anion of an ionic compound both being coordination compounds. You can see here this is essentially the same, but the metals have the different ligands. Here the chromium has the oxalate, here the cobalt has the oxalate. So if I give you a formula like this, you need to consider coordination isomers. And then we also have ionization isomers. If the counter ion, and most of the time those are anions, have the ability to be a ligand, such as sulfate or bromide, most anions have the ability to be that. And so you can exchange these two. And so you need to draw several sets of isomers. So this can become quite hard to do. Go to the homework and practice some of those, and as always, contact me. Hydrate isomers are similar to ionization isomers. In this case, the aqua ligand is a hydrate instead of the counter ion, so you're exchanging chloroligands with aqua ligands here. And so you should understand, if I give you a compound name like this, a formula like this, that you can potentially exchange these aqua ligands. So that can lead to excessive number of isomers. We also have linkage isomers. There are a couple that I hold you responsible for. One is the thiocyanato, and the other one is the nitro group. So SCN, which is thiocyanide, as a ligand is called thiocyanato, and they simply it used to be like thiocyanide and thiocyanato, or just the name. They would change the name of how it is coordinated. Now this is supposed to be a kappa, not a K, so there's something wrong with my Word or PowerPoint. But if it just kappa S means it's coordinated through sulfur. But for you, if I give you a formula recognizing SCN or NO2 minus nitro and nitrito, here's the example. It used to be called nitro or nitrito, depending on how it is coordinated. Again, this is supposed to be a kappa. So nitrito is the ligand either way, and then if the N is there, it's coordinated through the nitrogen. If the O is there, it's coordinated through oxygen. So I'm not going to draw and practice any more of these, but I want you to do this. Here's a couple of examples. There'll be 2 more on the next slide. And we have 2 and 2 and 1, that's 5. So here you go. You have to do the conformational isomers. I tell you specifically square pyramidal, but you may want to also go ahead and play around with just trigonal bipyramidal, just for practice. And then here I have one, I call it a triene. So this has 4 connections. But speaking of which, you should also practice using chelating ligands, right? Like En, knowing that this is ethylene diamine. And so if we were to draw that, and then we have an octahedral geometry, it is wise to use that chelating ligand, and since it can only go into the cis position, so you put it here just like we did with the 2 chlorals. We put them cis and we kept them put. I would do that with the chelating ligand and then play around with the amines and the bromos. And take note, because I am including here the bromide counter ion, that this can exchange with one of the chlorals. So there are several isomers you need to consider. So En or OX or DPPE are all chelating ligands that you might have to use, and you should know the abbreviations. And so all you have to do is for oxalate replace this with O. You can draw a little loop. DPPE is phosphorus, you know, and if you don't remember it and you don't have time to look it up, then you can just guess. As long as you recognize this as a chelating ligand, you should be in pretty good shape. All right, that's it for my introduction. When we come back, we're going to look at naming.